Okay, so last time we started talking about the properties of aquifers and went through essentially an introduction to groundwater. Today we're going to start talking about how groundwater moves in the subsurface. It's going to be a short lecture, couple example problems. Really, we're talking today about the flow of groundwater in one direction in an aquifer. This is happening all the time in the subsurface, but it is also going to form the basis of what we'll talk about next time, which is groundwater flow specifically to and from wells. So we're going to start with something you probably learned in geotechnical engineering, which is Darcy's Law. Darcy's Law says the flow rate is equal to negative K, the hydraulic conductivity, times some cross-sectional area, H1 minus H2 over L. And over here you can see a permeameter which you maybe used in lab. You have some cylinder with sand in it, a couple of piezometers showing the static head at two different points, flows coming through, and as it does you have some loss in head that you can measure there, and from measuring that head loss over the length and knowing the cross-sectional area, knowing the flow rate of water, you can calculate the hydraulic conductivity of this material. Okay, so if I take Q over A, divide both sides by A, I get this parameter little q, which is sort of a what we call a specific discharge, or the Darcy velocity. So Q over A equals little q, specific discharge, and that's negative K times the partial of H with respect to L. And so if K has units of length per time on here, and then you've got a distance divided by a distance, you can see that Q, little q, has units of length per time as well, which is a velocity. So in other words, the velocity of the flow is proportional to the hydraulic gradient, the difference in the heads divided by the length. Alright, so it's a velocity, but we call it a superficial velocity, right? So if you could imagine the different grains of material and the water moving past it, if you're going to track the water, a water molecule, it could actually be moving all around those grains, right? It could actually move around and back. It could go in circles around one and then around like this. That individual molecule of water might be moving much faster than what this little q velocity is. This little q velocity is essentially like the average bulk flow velocity through this cross section, right? Flow rate divided by cross sectional area. It's just how quick is everything moving through, even though on a microscopic basis the particles are all moving around. And so just keep in mind that the actual this linear velocity of a particle is always greater than that superficial velocity, which doesn't take into account what we call the tortuosity, or how tortuous the paths that those molecules might take are. So if we look at a confined aquifer, here's a little diagram of it. This part right here is where the water is. It's between these two confining layers. And we can look at what is the head over here and the head over here. Essentially, we have exactly the permeameter situation we have over here. Cross-section area is not changing. The flow is through some medium like sand or rock or whatever, and the head is dropping as we go. And so for flow in a confined aquifer, we get essentially this exact same equation that's up here. It's Darcy's Law. But we're going to use, we're going to do it on a per unit width basis. So just like we did in open channel flow, where we did a lot of flow per unit width into the page, we're going to do the same here. Okay, so this little q is the same as this little q, but we add a little prime to indicate that it's the flow per unit width into the page, and that's equal to K times B. Now B is sort of like little q is Q over A, and when we do a Q prime, instead of per cross-sectional area, we're doing per unit width into the page. So this becomes this A, instead of being a cross-sectional area, since we're on a per unit width basis, is just the thickness. So little q is going to be K times the thickness of the aquifer times the DHDL. So B is this thickness right here. So it's essentially a restatement of Darcy's law up here. In fact, you can use this equation or this equation, but typically we use this one. For an unconfined aquifer, it's not so simple because the thickness is not constant throughout the aquifer, right? The thickness is dependent on the water table. And the Dupuit made an assumption that this water table, we're going to assume that the hydraulic gradient is actually the slope of the water table. So you can remember from open channel flow where we talked quite a bit about in uniform flow we have all those slopes, the bottom slope, the surface slope, and the energy grade line slope, they're all the same. In non-uniform flow where the depth is changing over some distance, they're not the same. But in this case, we're making the assumption that even though the depth is changing as we move in the direction of flow, we're going to say that the hydraulic gradient, the slope of the energy grade line, is the actual water table slope. And so in reality, what happens is we have this a water table that might be a little bit curved like this. The Dupuit assumption results in us computing a water table line that's actually straight across. This isn't that important for a class like this to understand that this assumption is being made and that there's some error in that calculation, but depending on the circumstances, you can get large errors in certain cases if you don't recognize that that's the case. We're also assuming that the velocity is in one direction and it's this way, when in reality, because the depth is changing, the actual velocity is pointing downward a little bit. Okay, so the Dupuit equation says Q prime, again, the flow per unit width, it's equal to 1/2 K, and then we've got this H1 squared minus H2 squared, where H1 is the aquifer thickness or the water table height at one point, and then H2 is the water table height at another point, squared divided by L, the distance between those 2 points. Okay, and so where this can be used also, in addition to just flow in an unconfined aquifer as shown here, is if we had, say, like a levee or a berm, something that was separating a channel over here from a channel over here. This could be maybe an earth-filled dam, for example. We've got a higher water level over here, a lower water level over here. Water is going to tend to want to seep through this material from the high head to the low head, and we could use the Dupuit equation to figure out what is the flow of water through this this permeable object, this dam or whatever. Okay, so pretty straightforward equations. In the next 2 videos I'm going to do, or maybe 1 video, I'll do just a couple quick example problems so you can see how these are applied.